of the antiderivative. Again, this exercise is quite brief. Really, we're focusing on can we do the opposite of, usually I give you a graph and you have to draw the derivative graph. Now we're just working opposite. For our do-now question, we're looking at finding the antiderivative, finding an antiderivative, wording is very important, of 6x cubed minus 2x to the power of negative 2. Again, assuming it's negative 2, not negative 1. But we are just applying our general rule. So again, I am expecting proper mathematical notation. A lot of students will write this. You'll notice that, of course, we're writing antiderivative. I'm going to write this. And you'll even notice, let's just change, actually, no, let's leave that for now. We'll leave that for now. But we have integral of 6x cubed minus 2x to the power of negative 2. Please remember, you don't want to lose marks over this and forget your dx. Okay, of course, it's in terms of x. Students either make this mistake of not including dx. Every time you see this, you must include dx. Or the other mistakes are a lot of students make in the exams, particularly, is that if you're working in terms of, for example, you should be writing du or dy or whatever it is that you're working with, not dx, if that's the case. So just making sure that aligns with your question. Of course, we're separating this. I'm going to write that equals to, now 6x cubed, right? Of course, we're bringing the power up by 1, so I'm going to write 6x power 4 divided by our new power, which is over 4. We're applying the opposite of our derivative formulas. We're going negative or minus 2x to the power of, that's going to be negative 1, over bringing that, of course, over negative 1. What am I missing?
Plus c.
Thank you very much, plus c. Now the analogy, and I couldn't give this last time, but the analogy I'd love to give with calculating derivative and antiderivative is that when you calculate the derivative, it's like you dropping a ball in front of you. You know where the ball's going, you know where it lands, it's pretty easy, right? But if you're doing the antiderivative, you're throwing a ball into a field. You know the general direction, you know where it's going, but you don't know exactly where it's landing or where it has landed. With your antiderivative, you could be having a million different answers for the same derivative that you're working from. So with our antiderivative, we have plus c, c standing for, thank you very much, it just means a shift up or down, right? So just meaning our constant. Simplifying that gives us an answer of 3x power 4 over 2. And of course, because that is a positive, with the negative and the negative 1, that gives us 2, it should be positive 2 over x plus c. Now, why is this not the preferred answer, as in final answer? Does anyone know why this is not the preferred answer for a final response?
Is it because the x on the 4 is included in the fraction as well? We'll get to this side.
I'm okay. I don't think any assessors will care about that either. But that is a valid point. The reason why I don't think this is a proper answer is because the question asks for an antiderivative, so a specific antiderivative. This is a general antiderivative, isn't it? Because we're saying plus c. General, it could be any value. So you should really finish your response with, let's say, 3x divided 4 over 2 plus 2 over x. You can replace c with any number you want. That is an antiderivative. Right? But it's asking for an antiderivative, so we just give an example. If it says the general antiderivative, please don't write this. You must write the plus c. Later on, we'll learn about indefinite intervals. Why I give you specific numbers, and the plus c is not relevant anymore. But in this case, please keep the plus c. Okay. Any questions? Does anyone have any questions about why we have the plus c? Or is that pretty clear? Awesome. Just make sure you don't include the plus c when you're doing derivatives instead. Moving on to concept for today. It's really one major concept, and it's a little bit weird, but there are only a couple of questions for us to go through anyway. It's a little bit of a more niche concept. It's the backwards, just like with antiderivatives, solving the antiderivatives, the backwards of our derivative function. So we have here an example. If I give you a derivative function, can you give an example when it's moving backwards? So we're moving into the original f of x. I'm going to draw the f of x using this green marker. Hopefully you can read that off the back. I've got a table here that's from the textbook, right? And it really is just a key guide that you might want to refer to when you're drawing your graphs. This is specifically going from your differentiation function into your original function. And I've written it in short form, but if your line is, at that specific point, is positive and above, essentially, above the x-axis, then it's increasing. Pretty straightforward, right? If your derivative is above the x-axis, so it's a positive value, then gradient is positive, so it's increasing. Of course, the opposite applies as well. If it's below your x-axis, it's negative value, therefore it's going to be decreasing over time, isn't it? Okay? If it literally lands on the x-intercept, or it's a specifically x-intercept, then it's going to be a maximum or a minimum. Or rather, it's a stationary point. I should probably specify that as a stationary point, but there you go. If it's perfectly horizontal, which you don't see very often, it's just linear equation. An example of a horizontal line would be y equals c, right? Y equals 3, y equals 8, whatever it is. And if it's horizontal, when you anti-differentiate it, you're going to end up with a linear equation. So like y equals 2x, something along those lines. And then finally, if it's straight, so let's say it's a straight line, then you're going to get a parabola. A general rule applies. In this case, it's a parabola, isn't it? It's an upside down parabola. So I know that when I anti-differentiate this, it's going to be cubic, just by the fact that it's power 2. When I anti-differentiate, I'm going to increase the power by 1, it's going to be cubic, so it's power 3. So let's identify key points. I know that I have intercepts here and here. If it's an x-intercept, it's going to be a maximum or a minimum, but we've got to figure out, first off, where, and is it a maximum or a minimum? So let's start from here towards this point. It's negative. The gradient is negative. But you'll note that the gradient is going from a very negative point to slightly less negative. Negative point to slightly less negative. So I'm just going to go ahead and draw this. So very negative, slightly less negative, and then 0. If I go from here to here, right, I'm going from positive, or starting from 0, sorry. It's slightly positive, it's very positive, it's not very positive, and then back to 0. Okay, so again, it's starting from 0 to be slightly positive up to this point. It gets very positive, not so positive, but still positive, right? And then it brings us back into a stationary point, doesn't it? So it might look something like this, where it's very positive, sorry, slightly positive, very positive. Okay. So at no stage does it ever reach a negative point. I probably could have drawn that a bit better. Let's try that again. And then from that point on, it goes from 0 to slightly negative to very negative. So come back down. You might be wondering, well, how do you know that's like the height of my, I should say height, I should say y value. How do you know that's the y value of my stationary point? I don't, because it's possible for you to know. Unless you know like a key feature, like it intercepts at a specific point, it's impossible for you to know. So you're just drawing a general antiderivative. So I'm just following this table here, all right? We're keeping in mind that if whatever function I'm given as a derivative, I just increase the power by 1. If I'm given the derivative as a straight line, let's say it's a linear equation, then I just increase it and make it a parabola. Okay, so whatever you have, you just work backwards. Work backwards from your derivative functions, and just make sure you don't make the mistake of accidentally halfway applying your derivative, drawing your derivative graph rules instead. Any questions about that? Okay, that's pretty much it. There are only a couple of questions. There's only 8 questions to go through, most of which are multiple choice. So I'll let you give that a go, and then if anything, then you can catch up from previous exercises if